Lesson 3. Integer Types in Memory. A byte, or 8 bits, can be used to represent the integers 0 through 255, and we can add more bits to represent larger integers. However, we frequently need to represent negative quantities. To do this, we can take the larger half of the number range and wrap it around to the negative side, using what is called a 2's complement representation. For example, an 8-bit 2's complement representation for -1 has all of the bits equal to 1, and the representation for -128 has the most significant bit equal to 1 and the remaining bits equal to 0. We illustrate this with our first program, which is available on our lesson page at soax.net. In this program, we display the value 255, which has all of its bits on, and the value 128, which has only the most significant bit on. For clarity, we assign the values in hexadecimal, which is why we prefix the 0x to the values. Recall that hexadecimal digits convert easily to 4-bit nibbles. First, we output the values as unsigned chars and then as chars which are signed. The unsigned chars store values between 0 and 255, and chars use the 2's complement representation to hold values in the range from -128 to 127. Recall that we need to cast chars to ints to output integer values rather than the ASCII character. Pressing Ctrl and F5 to compile and execute the program, we see that the signed values of 255 and 128 are equal to -1 and -128 respectively. To fully describe 2's complement, we note that 128 converts to -128, and then we can convert the rest of the values up to 255 by adding the same thing to each side. Adding 127 shows us that 255 converts to -1, for example, as we already said. Likewise, 200 is 128 plus 72, so it converts to -128 plus 72, which equals -56. There's a simple method for converting bits to a signed 2's complement value. All we need to do is reverse the value of the most significant bit of the unsigned value. For example, in a byte, the most significant bit for an unsigned byte value is 2 to the 7 or 128. For a signed 2's complement value, we change this value to -2 to the 7 or -128. Flipping the value of the top bit to -128 subtracts 256 from the largest set of values. This sends the value to its equivalent mod 256. This modular equivalence means that all of the rules for arithmetic operate the same way. In other words, it doesn't matter to the computer whether the value it is calculating is signed or unsigned. As we noted, bite-sized numbers are computed mod 256, so 256 is equal to 0, and the additive inverse of a number, say 27, is 256 minus 27, or 229, which is -27 in 2's complement. Notice the similarity in the bit patterns between 27 and -27. You can get the additive inverse of a number by reversing the bits and adding 1. We can use 2's complement representations for any number of bits. With 2 bits, we could represent the unsigned numbers 0 through 3, or -2 through 1 in 2's complement. This is the conversion. For further illustration, we can create a table for 3 bits with the ranges 0 through 7 and -4 to 3 for unsigned and signed integers respectively. Integer types come in a variety of different ranges. You can take a look at our C++ console lesson 24 for a list of the fundamental data types and the range of values that they can take on. In our next program, we use the size of operator to display the sizes of some integer types. We have included the bool and char types because they can be used in much the same way as integers. Executing this program, we see the sizes of various integer types. All of these types, except for bools, have signed and unsigned variants. The sizes are given in bytes, and we should point out that 2 bytes or 16 bits is called a word. 4 bytes or 32 bits is a double word, and 8 bytes or 64 bits is a quadruple word. This is the terminology that is used by Microsoft inside of Windows, but the terminology differs on other operating systems. For our final program, we want to show how a multi-byte integer type is stored across byte-sized memory locations. For this program, we use an unsigned 32-bit or 4-byte int type and assign the most significant byte the value 6, the next one 7, the next one 9, and the least significant byte 4. We start by printing the size of the unsigned int, its address, and its decimal value. Then we run a loop over the 4 bytes of the unsigned int and print the byte index, the value that it holds, and finally the address of the byte. We use chars to access a single byte at a time. Executing the program, we see that the size of the unsigned int is 4 bytes, and its value is roughly 100 million in decimal. Looking at the bytes, we see that the least significant byte is first in memory, and the most significant byte is last. This is called little endian ordering. Other operating systems put the bytes in the opposite order, which is known as big endian order.